Welcome back, all of you. So, in this video, we'll study about different types of signals. We'll begin with singularity functions. Okay, so the different types of singularity functions are your unit step functions, unit impulse function, and unit ramp function. I hope you have some idea about all these signals. So, in area of communication systems or signals and system, these three functions, unit step function, unit impulse function, and unit ramp functions, they play a very important role because they serve as the basis for representing the other signals. They serve as basis for representing other signals. Now, why they are called as singularity function? These three functions, unit step, unit impulse, and unit ramp functions. These three signals are known as singularity functions because singularity is basically a point at which a function does not possess a derivative. So we can define singularity. Singularity is a point at which function does not possess a derivative. So each singularity function has a singular point at the origin and is zero elsewhere. So each singularity function has a singular point at the origin. So these three functions, unit step function, unit impulse, and the unit ramp function, all these three are singularity functions. What is singularity? It is a point at which the function does not possess a derivative. And each singularity function has a singular point at origin. That means all these signals, unit step, impulse, and the ramp function, they don't have the derivative at the origin. So let us begin with the first type of signal, that is unit step. So it is usually denoted by u of t in if you are talking about continuous time signal, and u of n if you are talking about discrete time signals. So let us first define continuous time unit step function. U of t can be mathematically defined as its value is 1 for t greater than 0, its value is 0 for t less than 0, and for t equal to 0 it is a singular function at the origin. So its derivative is not available at t is equal to 0. And its usual value considered is 1 by 2. In many books you will find this value to be not defined. This value can also be said to be not defined. And in some of the books you will find the value of unit step function in continuous time at t is equal to 0 is 1 by 2. Okay, so if we try to plot this function u of t, you can see that with respect to time, its value is 1 for t greater than 0, and for t equal to 0 it is not defined, or you can say 1 by 2. Now moving on to the discrete time unit step function, u of n can be simply defined as 1 and 0 for n greater than equal to 0 and n less than 0. And if we try to plot this function, we'll have discrete values. All the values will have to as 1. So this is how we define a unit step function. It is a singular function. Its derivative is not available at t equal to 0, that is origin. And for continuous time signal, continuous time unit step signal, the value at t equal to 0 is 1 by 2 or not defined. For t greater than 0, it is assumed to be 1. For t less than 0, it is assumed to be 0. Moving on, we'll next discuss unit impulse function. These three singularity functions, unit step, impulse, and ramp functions. These are really important. The reason being that these functions forms the basis to represent other signals in your communication systems and your sequencing systems also. The continuous time unit impulse function is also known as direct delta function. And the conventional definition of unit impulse function is that it is usually represented by delta t. So mathematically we can define delta t as 0 for t not equal to 0, and area under the unit impulse curve is unity. Area under the impulse function is unity. And if we want to plot this function, you can see the plot of this function also. See this unit impulse function delta t. It is usually regarded as a rectangular pulse with a width that is approaching towards 0. It is nothing but a rectangular pulse whose width is approaching towards 0. You can easily approximate a rectangular pulse into an impulse function by assuming its width approaching towards 0, and the height of pulse is adjusted such that the area has to be maintained at unity. That means the width is 0 and the height is adjusted such that area is equal to unity. And actually the important feature of this unit impulse function is not its shape, but the fact that the effective duration, or you can say the pulse width, approaches 0 while its area remains unity. So the pulses such as rectangular pulses, or you can say the exponential pulses, triangular pulses, and many other pulses, they may be used in impulse approximation. These pulses can be approximated to a impulse function. We may also generalize the unit impulse function. And the reason for the generalization is that if you look at this above equation, that is delta t equal to 0 for t not equal to 0. So if this equation is valid, then we can say that k times of delta t will also be equal to 0 for t not equal to 0. Correct? But here the area is what? K. Area here in this case will be k. So we'll call this k times delta t as an impulse function whose area is k. So this can be called as an impulse function with area k. Next, we'll discuss some of the important properties of continuous time unit impulse function. Properties of continuous time unit impulse function. The very first property is shifting property. Let us see this shifting property. The shifting property is defined as if we multiply xt, any arbitrary signal xt, the unit impulse function delta t, and integrate it over the infinite range, then the resultant is your signal xt at t equal to 0, or you can say simply x of 0. So this is your shifting property. We can easily prove this property, like if you're multiplying any arbitrary signal x of t, I will just draw any arbitrary signal x. Say this is a continuous time arbitrary signal x of t. It is getting multiplied with the impulse function delta t. Impulse function, we know it is function which is delta t is equal to 0 at t not equal to 0. If you multiply these two, what will be the resultant? The output signal will be 0 for t not equal to 0, isn't it? And what will be its value at t equal to 0? 1 multiplied by this value. What is this value? This value is nothing but x of 0, right? So the resultant will be x of 0 into delta t, right? Now if we take integral of this multiplication over an infinite range, the integral is multiplied over infinite range, we're left with this, right? X of 0 is a constant value, it can be taken out of the integral, so we're left with x of 0 and integration delta t dt, and we already know that this area under the unit impulse function is nothing but unity, so this is equal to x of 0. In this way you can easily prove your shifting property. Moving on, the second property for the unit continuous time unit impulse function is the scaling property. Okay, so we can define scaling property as del a of t. If you scale the time independent time variable, the resultant will be 1 over modulus of a times of delta t. Again, you can easily prove this property. I am not going to the for this. You try it on your own. Third property is the impulse function is an even function. This is the third property that is represented mathematically as del of minus t is equal to del of t. Next, we'll look at the properties of discrete time unit impulse function, which are slightly different from that of the properties of continuous time unit impulse function. Properties of discrete time unit impulse represented by delta of n and defined as delta n equal to 1 and 0 for time greater than equal to 0 and less than 0. Right? This is how we define a discrete time unit impulse function. So the very first property says that this scaling property in case of the continuous time, that is delta times k of n is equal to delta of n. where k is any integer value. Okay. And it is quite intuitive because we know that delta n is equal to 1 0 for n greater than equal to 0 and n less than 0. So if in this definition we replace n by k of k times of n, to become 1 0, this will remain unchanged, and the range will also now become k of n greater than equal to 0 and k of n less than 0, which is nothing but n greater than equal to 0 or n less than equal to 0, isn't it? So we are left with what? Here, delta n. So in case of scaling in discrete time pulse function, del k n is equal to del of n. The next property of discrete time unit impulse function is that delta n can be represented in the form of a unit step signal. That is, delta n can be represented as u1 minus u of n minus 1. This is the second property, which can again be proved very easily. If you got u1 and u of n minus 1, subtract them, you will see that you are left with only del of n. Third property states that for any arbitrary sequence x of n, x of n multiplied by shifted version of the unit impulse, discrete unit impulse, is equal to x of k del of n minus k. This is your third property. So this is all about the unit impulse function. You've seen the properties of continuous time and the discrete time unit impulse function also. Now moving on to the third type of the signal, that is the unit ramp function. It is usually represented by r of t for continuous time and r of n for discrete time. Let us define one by one both these mathematically. R of t is equal to t times u of t, and that can be said as t for t greater than equal to 0 and 0 for t less than 0. And similarly, the discrete time version of unit ramp function, that is r of n, it can be defined as n times u of n, which is equal to n for n greater than equal to 0 and 0 for n less than 0. Let us see the plot of these two RT and R of n. So RT is a ramp function starting from 0 with slope 1, and R of n is a discrete time function, right? Starting from 0 with 1. This is how we define the unit ramp function. Okay, so next we'll look at the relationship between these three functions. A relation between unit step, impulse, and ramp functions. Right. So these relations are really very important. Derivative of the unit step function is equal to the unit impulse, or we can say that u of t unit step function is equal to integral of the unit impulse function. Similarly, we can say that derivative of the unit ramp function is is equal to the unit step function, and vice versa, that is the ramp function can also be defined as the integral of unit step function. These are two very important relationships between unit step, unit impulse, and the ramp functions. Okay, so far we have discussed about the transformations of the signal and three different types of most commonly used signals like unit step, impulse, and ramp. Now let us club these two topics and try to do one question. The question is draw the waveforms of the following signals. So we are given with 9 signals over there, and all the signals are in the form of unit step function u of t. Alright, so I'll discuss this part, G part, and let's say this I part. The rest of the questions you can practice on your own. So let us discuss first part G. The question is, the signal is given x of 7t, which is u of t minus twice of u t minus 1 plus u of t minus 2. Aim is to draw the waveform of this function x of 7t. We know the waveform of ut. All of us know the waveform of ut is yes. So this first part is already known to us. No need to derive this. Let us find out the second part, which is a part. Second part is u of t twice of u of t minus 1. T minus 1, that means we have to apply the shifting transformation over here. So it is t minus 1. So the waveform will be shifted towards the right on the time domain axis, and the shift will be by 1. Alright, so this is ut. We have to shift this is ut. We have to shift this waveform by 1 towards the right side. So this becomes u of t minus 1. And if let's say this amplitude is 2, then it becomes twice of u of t minus 1, which is our second term. So this becomes our second term. Now moving on, we can also draw the third term, that is u of t minus 2. It is again an example of your shift and transformation, and the shift is here by 2, right? So we'll shift ut by 2, which becomes like this, amplitude will be 1. Alright. Now we can club these three parts. That means in the question we are given that ut, which is a, minus this term b plus this term. Okay, so let us subtract first a minus b. So if you subtract a minus b will give us what? ut minus twice of u of t minus 1. And if you look at it graphically, the subtraction of these two terms, the resultant will be one. See, from 0 to 1 on time axis, 0 to 1, we subtract a minus b, the resultant will be only 1, because this signal b is 0 from 0 to 1. So we have done the same thing from 0 to 1, the resultant is 1. And now beyond 1, this b waveform is, the amplitude is 2, but this remains 1. So a minus b beyond 1 will result into minus 1. That is what we have done here. Now the next step is to add the term C to this waveform, A minus B waveform. That is A minus B plus C, which becomes UT minus twice of UT minus 1 plus plus U of T minus 2. So now let us add this term C to this waveform, and let us see what we get. Alright, so this is what we get when we add this C waveform to the waveform that is A minus B. You can please verify this answer also. It is the same thing. Now moving on to the next part, which is the ith part. Ith part was x of 9 t is equal to derivative of x70 dt. Right. So we know the x70, we have just now implemented x70, that is this ut minus twice of ut minus 1 plus ut minus 2. So it becomes derivative of ut minus twice of 2 minus 1 plus u of t minus 2. So now if we take the derivative of this entire term by term, so it becomes derivative of ut, unit step function, which is an impulse function, del of t. What was the second term? Derivative of twice of ut minus 1 is twice of del t minus 1 plus del of t minus 2. Now we have to plot this term, which is x of 9. Right? So just plot it on this waveform. The first term is del of t, which is this. Second term is minus 2 times del t minus 1. We have to now use the shifting transformation, shifting delta t by 1 towards right on the time domain axis, and its amplitude will be multiplied by minus 2. So we shift the pulse by 1 and the magnitude is minus 2. Third term is del t minus 2, that is again shifting transformation. We shift the impulse function by 2 and the amplitude is 1. This is the waveform of x9t. Similarly, you can try all the given questions over here. All these are the transformations of a unit step function. Similarly, for your practice, you can try these questions as well. These 6 questions, which are again on the same pattern, that is, you need to draw the waveforms of all these 6 signals, which are combination of the ramp signal, and unit step signal. So this will give you a very good picture of the signal transformations and the properties of ramp and unit step functions. So that is all in this video. We can take up any doubts if you have in the next upcoming live session. Thank you so much.